Hi and welcome. This is the third part of a tutorial on file handling in C#. In the last video on file handling, the focus was on handling text files in C#. This video will focus on handling binary files in C#. This tutorial is the 22nd part of a beginner's course on C#. Once all the videos on file handling have been released, this will mark the end of this C# for beginners course. The next course produced by this channel will be a C# advanced course. So please consider subscribing and ring the bell so as to be notified of future videos. Let's start by gaining a basic understanding of what is meant by binary files and what is meant by text files. A binary file stores information in a binary format, ones and zeros. You could argue that a text file is also ultimately stored in ones and zeros, and you'd be right. The main difference is that a binary file stores data that is computer readable and not easily human readable. A text file stores data in a human-readable format, usually ASCII. ASCII is an acronym for American Standard Code for Information Interchange. It is a code for representing 128 English characters as numbers, with each letter assigned a number from 0 to 127. For example, the ASCII code for uppercase M can be represented as a decimal value of 77. So let's traverse the subject of binary file handling in C# by creating a code example. At points during the code creation process, I will need to go fairly quickly, so that I can cover a fair amount of ground in a timiest fashion. As always, the code can be downloaded from GitHub so that you can go through the code at your own pace. A link to the appropriate GitHub repository is available below in the description. In this basic code example, we'll create a binary file with a .dat file extension named employees. This file will be used for storing employee records. The functionality within this application will simply add 3 employee records to the binary file using C#'s BinaryWriter class. These 3 records will be retrieved by our code using C#'s BinaryReader class and displayed to the console screen. Random access file handling code to update an individual field within an employee record will be created through the use of C#'s BinaryWriter class, as well as C#'s FileStream class. So let's start by creating a .NET Core console application. Let's name this application Binary File Handling. Let's create a class named Employee and create 5 properties. Within the employee class, let's define a constant named nameSize and assign it a value of 20. You'll see the significance of this constant in a bit. Let's define an auto-implemented property named ID, which is defined as an integer. Let's create 2 private variables defined as strings for the employee's first name and last name. Let's create first name and last name properties to encapsulate these private member variables. Notice in the get part of these properties that we are using a ternary operator to ensure that the size of the strings returned by these properties are always 20. This is because these values are going to be written to a binary file, and we want to be able to access and update the individual fields through our code. So if we want to perform random access file handling on our binary file, we need to know the size in bytes of each record and the size in bytes of each of the fields that exist within the records. Through code, we can ensure that the records are of a fixed size. So in this particular case, we are fixing the size of the first name and last name properties to a length of 20. Let's create 3 auto-implemented properties for salary, gender, and isManager, which are defined as decimal, char, and bool, respectively. So let's create a variable in our main method that will store the calculated size of each of our employee records. Note we are able to use the sizeOf method on the value types, and for the first name and last name properties, we are using the employee.nameSize constant to calculate the size of an employee record. The size of a record is measured in bytes. Let's write code to establish the name of the binary file that will be used to store our employee records and the path where the binary file will be stored. Notice there is a red squiggly line under the path class reference in our code. The path static class is a member of the system.io namespace. Let's include a directive to this namespace at the top of our code. So let's write a method named seedData that will be responsible for writing 3 records to our binary file. Let's write code to test whether the binary file exists. If the if statement condition is true, we want to create 3 employee objects and write the values we have assigned to their properties to our binary file. Let's make sure our seedData class resides in the program class and has a private access modifier. Let's create another private static method that will be responsible for writing an employee record to our binary file. Let's name it addEmployeeRecord. So now we can use the writer argument, defined as the BinaryWriter type, to write our employee object's property values to our binary file. Let's go back to our seedData method and call the addEmployeeRecord method 3 times to add 3 records to our binary file. Notice that the BinaryWriter object is instantiated within a using statement, and our code that writes the records to our binary file is executed within a using block. This functionality is elegant code syntax provided in the C# language that ensures that once our file handling code within the using statement is finished, that the relevant file is closed and that the memory space that was taken up by the object instantiated within the using statement is freed. Behind the scenes, as it were, the close method and subsequently the dispose method is executed for this purpose. In the interests of formatting, let's create methods responsible for establishing text for a main application heading and a heading for a table containing employee records. Then let's create a method for displaying these headings to the console screen. Now let's create a method responsible for displaying all the records retrieved from our binary file. We'll use the BinaryReader class to read each field in each employee record from our binary file and write their values to the console screen. Note that we are able to traverse the values of our record by reading the appropriate field values based on their type. For example, we can use the readInt32 method to read the value of the ID field. We can use the readString method to read the value of the first name and last name fields. We can use the readDecimal method to read the value of the salary field, etc. Note that each time the relevant read method is called, a pointer to the next field in the binary file is shifted by the number of bytes taken up by the previous field. So now we need to create a few ancillary methods so that our code knows how many employee records exist within our binary file. The getFileSize method returns the file length of our binary file, i.e. the size measured in bytes. The getNumberOfRecords method returns a value calculated by dividing the file size in bytes by the size of each record, also in bytes. So this calculated value is the total number of employee records stored in our binary file. We can then call the display all records on screen method from within the show main screen method. And then call the show main screen method from the main method. Let's run the code. Oops, I forgot to call the seedData method from the main method, so of course the binary file does not exist. Okay, so I'm going to change the name of our file from employee.dat to employees.dat. Seems more appropriate. And let's try again. And this time we get a system.io.endofstream exception occurring. And this is because when we are reading the field values stored in the binary file, the field lengths are not matching up with the length of the field values stored in the binary file. Let's see why this is occurring. Okay, the problem is that I forgot to write the gender field to the binary file. Okay, so the data in our employees.dat file has now been corrupted from this bug. Now that we have fixed the code, let's delete the employees.dat binary file so that a new employees.dat file will be created from the code that we have just updated with the appropriate bug fix. Let's try again. Okay, so that looks pretty good, but I've noticed that the ID value next to the third record displayed on the screen is the same as the ID in the first record displayed on the screen. So this requires a simple fix, and we can implement this a bit later. But the basic code for using the BinaryWriter class to write records to our binary file and the BinaryReader class to read records from our binary file has been successfully created and tested. So let's open our employees.dat file in Notepad, and you can see that most of the fields are not human readable, and this is because this is a binary file and not a text file. We are writing values stored within native C# types to our binary file and then reading these values from our binary file and populating appropriate C# types with the appropriate values. Okay, so let's create code to allow the user to update the individual fields of a chosen employee record and save the user's updates back to our employees.dat file. So let's create a method named updateEmployeeRecord. Let's create a variable named totalRecords and assign this variable a value that is returned from the getNumberOfRecords method. As the name suggests, this variable stores the number of records currently stored in the employees.dat file. Let's create a new method named findRecordById. This method will return a value to the updateEmployeeRecord containing the byte position of a record stored in the employees.dat file. By traversing the record stored in the employees.dat file, reading the ID of each record, and if the employee ID inputted by the user matches one of the IDs of a record stored in the employees.dat file, the byte position of that particular record is returned to the calling code. Okay, let's create a method named getRecordPosition, and this method simply returns a calculated value, which is the record size divided by the ordinal position of a particular record. The variable storing this value is named position. This method essentially returns the byte position of a particular record in the employees.dat file. This method is called within a for loop which traverses the number of records currently stored in our employees.dat file. So once we have this byte location, we can use the FileStream object seek method to move the pointer to the appropriate location in our binary file. We can then read the ID using the readInt32 method on the BinaryReader object to read and assign the ID value of the record to a local integer variable named readID. Then we can compare the readID variable containing the current ID value extracted from the employees.dat file to the user's inputted ID value. If the user's input matches the ID of a particular field, the byte location offset from the beginning of the binary file to the beginning of the record with the matching ID is returned to the calling code. If the record is not found in the employees.dat file, a value of -1 is returned. Then in the update employee record method, let's call the find record by ID method. If the value returned by the find record by ID record is not -1, a matching record based on the user's inputted ID has been found and the byte position offset from the beginning of the file to that record is returned. We are storing the byte position of the matching record in a local integer named pos. If pos is not -1, we are going to use an instantiated object of the FileStream type to navigate to the relevant record in the binary file so that we can write the user's input over the relevant field stored in the employees.dat file at the relevant position of where the matching employee record is stored. Note that in the seek method called on the FileStream object, the offset parameter is being passed an argument that includes the position returned from the find record by ID method, plus the size of the ID field, which is stored as an integer. This is because we do not want the user to be able to overwrite the ID field. This should be an auto-generated unique field. Note we have not implemented codes to auto-generate unique IDs in this application. If you download the code from GitHub, I recommend writing code to add a new record to the employees.dat file with an auto-generated unique ID as a great exercise. If you choose to do this and get stuck, please drop me a comment and I'll get back to you as soon as I can. So I'm now going to write methods for each of the updatable fields. Let's include code for each of the updatable fields to first assess if the relevant field has been left blank by the user. We are using the isNull or whitespace method here to assess whether the user has left a particular field blank. If the user leaves the field blank, we don't want to overwrite the current field value in the employees.dat file. In this case, we do need to include code to direct the pointer maintained by the FileStream object to the next field. We do this by implementing the seek method on the relevant FileStream object. If a valid value is entered, however, we can write the user's input over the relevant field in the employees.dat file, and the pointer stored in the relevant FileStream object will automatically be advanced to the position of the next field. So let's now call the update methods implemented for each of our writable fields within our update employee record method. Let's finish writing the code in the main method. I'm going to fast forward this process. Note that I've included very basic exception handling in this code example. In a real-world application, I would encourage you to implement exception handling properly and not like I have done here with a catch-all exception catch block in the try-catch block within the main method. For guidance on how to handle exceptions in C#, a link to a playlist containing videos on C# exception handling has been included below in the description. I'm going to apply a fix to the last record where the ID field is currently not unique. I'm going to also delete the employees.dat file so that a new employees.dat file is created from the code containing the fix I've just applied. Let's run the code. So let's say that Sarah has recently married and we need to change her last name to Jones. Great. Let's say that Bob has recently been promoted to manager and that he has also been awarded a salary increase. Excellent. And let's say that Andy has decided that he prefers to be called Andrew. So let's change his first name to Andrew. Excellent. Great. So I know I went through this code fairly quickly, but I felt I needed to cover a lot of ground and didn't want to spend an inordinate amount of time on binary file handling. If you feel you have benefited from this tutorial, please hit the like button and please consider subscribing. Please ring the bell so that you can be notified of future content, which will be coming soon. And please feel free to download the code created in this video from the relevant GitHub repository. The next video will focus on memory streams in C#. Thank you and take care.